going to see with equilibrium, there's actually several different flavors of equilibrium constants, okay? So with this little subscript letter right here, right, we're going to play alphabet soup with the equilibrium constant. And by the end of this semester, we will actually have Ka, Kb, Kc, Kd, Kf, Ksp, Kp. So we're going to have lots of these different types of flavors. So once again, we remember that C stands for concentration. Okay, so I'll write that down. And our units for equilibrium concentration are in molarity. Well, what does the P stand for? Well, as you might guess, that stands for pressure. Okay. So here we've got the Haber-Bosch process for making ammonia. So that's a nitrogen molecule plus 3 hydrogen molecules. And as you can see, this is definitely an equilibrium reaction, makes 2 NH3s. We can write down Kc in our usual way. So products over reactants. Now we write this as NH3 squared because there's the 2. N2 raised to the first power and H2 raised to the third power, okay? Well, we can write Kp in the exact same way, but now all of these P's right here, so for example, P sub N2, that is the partial pressure of whatever species we're talking about, right? So I'll say of dot, dot, dot. So if we were doing this, you notice here, these are all gases in this reaction. So it actually makes a lot more sense to use Kp for a gas phase reaction because we're all going to fill these things into a container using some type of pressurized cylinder, right? So we might have so many atmospheres of ammonia and so many atmospheres of nitrogen and so many atmospheres of hydrogen, okay? So we use those pressure units when we're talking about Kp, right? We also have a way of interconverting between Kp and Kc because they're not necessarily the same value. So you don't have to memorize this equation that I'm boxing right here. I'll give that to you in an exam, but you do have to know how to use it, okay? So for example, if let's say we have Kc from our molarities, okay? We can convert that into Kp by multiplying the Kc constant by the constants R and T. So we remember R is the gas constant, 0.08206 liter ATM per mole per Kelvin. Okay, and so that means, of course, these partial pressures need to be in atmospheres. This temperature right here, this is the temperature of our reaction, temp of Rxn. So as it turns out, the reaction temperature matters for the equilibrium constant. And now this delta N right here, this is the difference between the stoichiometric coefficients. So you can see right here, delta N I've given right here. And I'm using, once again, these lowercase letters that are connected to the stoichiometric coefficients, okay? So really, this delta N is the sum of the products minus the sum of the reactants, right? So this C plus D, we add up the stoichiometric coefficients for the products. And then we subtract that from the sum of the stoichiometric coefficients of the reactants, okay? So let's do an example of just writing this expression, okay? So NO2 gas dimerizes to form N2O4 gas. Come up with a balanced reaction first, then write the equilibrium expression with respect to Kc and Kp. Okay, so what does that mean to dimerize? So I always like to challenge you guys with using some actual chemistry lingo. So if we just say NO2 forms N2O4, oops, not aqueous, it's gas, because it says N2O4 gas, right? And then we note that because it says it has an equilibrium expression, it's a forward arrow and a backwards arrow. So as you can see, to make this balanced, we just need to put a 2 right there. So that's really what dimerizing means. Something reacts with itself. Okay. So now I could write this for Kc. And writing this for Kc, I would use the brackets N2O4 and raised to the first power. Okay. So I don't have to write that down. And then now divided by NO2 all squared. Okay, great, easy. So how do I write Kp? Well, I just write P sub N2O4. So that's the pressure, partial pressure of N2O4 in a mixture between N2O4 and NO2. And then I'd write P sub NO2 and then all squared. Okay.